When equal distances, delta S, along the circumference of a circle, are traversed in equal time intervals,
You might want to take
the
some notes
motion
along
is
the way,
called
too.
uniform circular motion. The linear speed, v, is equal to delta S divided by the corresponding time interval delta t, and is constant. The linear velocity, however, is not constant. As the motion proceeds, the velocity vector changes its direction continually, being always tangent to the circle, or what amounts to the same thing, perpendicular to the radius. Because of the changing direction of the velocity vector, uniform circular motion is accelerated motion. In a small time interval, the vector v1 changes to v2. The difference between v2 and v1 is the vector which must be added to v1 to get v2. Another way of finding the vector representing the change of velocity is to add to v2 the negative of v1. The sum of these vectors is v2 minus v1. The change of velocity during any time interval is the vector v2 minus v1, or delta v, and is seen to point inward somewhere near the center. When the 2 points are closer together, delta v points toward a place nearer the center. When the 2 points are extremely close together, delta v always points toward the center. And therefore, the fraction obtained by dividing the vector delta v by the scalar time interval delta t is a vector pointing toward the center. The limiting value of this ratio, as both delta v and delta t approach 0, is by definition the acceleration vector a. Since vector a points toward the center, it is called the centripetal acceleration. The velocity vector and the acceleration vector are always perpendicular to each other, v being directed along the tangent and a along the radius. Having found the direction of the centripetal acceleration, let us now proceed to calculate its magnitude. We again choose any 2 points on the circle. The angle delta theta between the radii is the same as the angle between the velocity vectors. This follows from simple geometry. The magnitude of the vector delta v is small delta v, and the magnitude of both vectors v1 and v2 is small v. If points 1 and 2 are extremely close together, the vector triangle and the space triangle are similar triangles. Corresponding sides are therefore proportional, or small delta v is to small v as delta s is to r. Therefore, small delta v equals small v over r times delta s. Dividing both sides of this equation by delta t, the time interval that it takes the body to go from point 1 to point 2, we get small delta v over delta t equals small v over r times delta s over delta t. As points 1 and 2 are taken nearer and nearer together, small delta v over delta t approaches the magnitude of the acceleration a. Delta s over delta t approaches small v. Therefore, a equals v squared over r. If a mass m has an acceleration a of magnitude v squared over r and is directed toward the center of a circle, then, since we believe that Newton's second law applies to this kind of acceleration as well as to all others, we say that F equals ma, or F equals mv squared over r, and is directed toward the center. This force acting on the body, necessary to keep the body moving in a circle,